Hi and welcome. My name is Dr. Jane Kuparis, and I'm going to be working with you today as part of the Pursue project on looking at pre-processing our electrophysiological data. Before we get started, just to give you a sense of how these videos work, at first I'm going to give you just a brief overview of some of the theory and the reasons why we're doing what we're doing with the data. And then the second part, I'm going to walk you through the practicalities of actually processing the data in EEG Lab and ERP Lab within the MATLAB platform. So we're going to go ahead and get started. We're going to be talking about filtering today. But before we do that, I just want to give you a really broad overview of pre-processing as a whole. The idea is we want to get our raw data into a format that we can look at it. So we need to first reduce some of the noise that's in our data. Then we'll be transforming it so we can compare it across conditions or trials. We also need to extract segments from our EEG data because EEG data is just continuous. It's very long, right? And we want to break it up into those trials and into those different conditions. And then finally, that will allow us to average across our trials and conditions so that we can actually look at our data and look at it in comparison, compare different conditions, and associate it with different cognitive functions. To do this, there are a number of different steps. The order of these steps is today we're going to be using for DC data. If you have AC data, you might do these in a slightly different order, but we're going to be focusing on this particular order of operations for today, starting with filtering the data. But before we even get to filtering the data, because we have DC data, we have to do something called a DC offset. This is taking the average of the entire recording and shifting the recording so it averages out to 0. We want to do this because depending on where we're recording, we might be starting at a different level. It's just a voltage, high or low. And so we want to make sure that all of them are averaging out to 0 so that we can kind of bring them into alignment with each other. If we don't do this, we may have trouble looking at our data in comparison to each other. So when we first open up a file, if we haven't done the DC offset and we're using DC data, you may see that the different electrodes are producing electricity that are in very different ranges from each other. Doing the DC offset really brings them into alignment. So it's important to do that if we have a DC recording. Once we've done that, we can actually do our major first step, which is filtering. The reason we filter our data is because we want to be able to visually interpret and inspect our data better, but also we just want to get rid of noise that is not brain activity. We want to get rid of things like electricity in our environment produced by lights or cell phones or what have you. In the United States, that's often at around 60 hertz, but if you're in Europe, it might be 50. We also want to get rid of some muscle movement noise, which is high frequency, and low frequency activity like skin potentials. We want to get rid of these because brain activity is really only occurring between about 0.1 and 30 hertz. And so we want to reduce all the higher and lower frequency activity from that as best we can. We can do this in a number of ways. We can use filters. There are different kinds of filters, for example, analog filters, but today we're going to be using a frequency filter. Frequency filters are kind of like coffee filters, right? You really want good coffee. So coffee filters allow the coffee to pass through and block those unwanted grounds that really wouldn't taste very good. The way that we do this is we set a threshold that allows certain frequencies to pass through or be retained, and we block the unwanted frequencies or attenuate them, make them smaller. There are 4 primary ones that you can use. There are more than just these, but these are the ones we're going to talk about today: low pass, high pass, band pass, and notch. As I mentioned, different data systems can be processed in different orders. Some things can happen in any order. Other things have to happen in a certain order. This is one of those steps that you can put kind of anywhere. You can filter at the beginning, you can filter at the end. In our process, we filter at the beginning because you do the DC offset within that filtering process. And so it's a good time for us to do that. We're going to start with the low pass filter. The low pass filter only lets frequencies below the threshold to pass through. the data and allow them to stay. The way I tend to think of this is that if you've got a gate, only some things can get under that gate. A giraffe that's really tall could not, but a mouse could scurry on through, right? Low pass filters in general are used to reduce electrical noise and EMG noise, or muscle noise. What this actually does to our data is imaged here on the right side of the screen. We start out with some really jaggedy black lines, right? And those little jaggedy things are the high frequency noise. We use a filter, it smooths out and it looks more like the red line. And this allows us to see more of the general peaks versus those little tiny peaks. As we're deciding what kind of filter we want, or what threshold we want, I should say, we think about how much we're letting pass through. It's not an on and off switch as much as people would like it to be. Instead, it is letting different amounts of different frequencies through. So the image on the left-hand side of this screen shows you that below about 30 hertz, the amount that's getting through is more. And on the right-hand side, the amount that's getting through is less. You don't really need to understand what passband gain means. All you really need to understand from this is the farther you get along, the higher the frequency, the less that is getting through. And that's what you want. And the half amplitude cutoff is where about 50% is getting through. And that's what we want. And that's what we're setting for our MERC. High pass filters only let frequencies higher than the threshold to pass through. And so I like to think of this as trying to get over something. You have to get high enough in order to get through. One limitation with high pass filters is they can create some artificial peaks and reduce parts of the wave that you're interested in. So this is a really good reminder that you always want to look at what you're doing. So in this case, you want to look at what your filter is doing to the data to make sure it's not causing problems and it's actually doing what you want it to do. High pass filters are mostly used to reduce slow changes in voltage. These are things like skin potentials that are much lower in frequency. What it actually does to your data, you can see kind of in the right-hand image. So the higher your high pass filter, kind of the more squat your actual waveforms get. So it will reduce the amplitude of your waveforms the higher you get. And if you're interested in a small high-peaked component, this may not be a good idea. So you want to think about how much you want to increase your high-pass filter because of this effect. On the left-hand side, you can see two examples of how you might image or imagine this actually happening. The upper one is more like the image we saw before. The lower one is more like you might see in an actual program because they're such small numbers that it often looks like it's a straight line, but in actuality, it's more of a curved effect. It's not on or off, just like the other kind of filter. If you put together both a low pass filter and a high pass filter, what you get is a band pass filter. It's letting some stuff in that's below one and above the other. And so you have this nice middle range that you could be in. And so we'll be using this one today, but this is a common way to do your filters. Another common one you might see is something called a notch filter. This cuts out a very small notch of frequencies, and this is often used when you know you have a lot of electrical noise in particular. So for example, if you have some fluorescent lights that are creating a lot of 60 hertz noise, you might just use a notch filter to try and get that out, but save as much of the other data as you can. And so that's when you might use this. So we do have these four types of filters in particular: low pass, high pass, band pass, and notch filters. There are others, but these are the ones that we're most concerned with today and we're going to look at. So with that, I'm going to change my share to looking at MATLAB. Actually, I'm going to show you my entire screen because it turns out it is easier to see things when I do that. And since this is our first video, I'm going to walk you a little bit slower through the opening up of a file because sometimes that can be problematic, but then we're going to move right on. So the first thing you do when you open MATLAB is you need to set a path to where your plugins for MATLAB are for EEG Lab and ERP Lab. So you're going to use this Set Path button. It may be in a different place on your computer, but look for Set Path. And then you're going to go to Add with Subfolders. The reason you don't do Add Folder is you're going to miss all of those folders that are in it that you actually need. So you're going to use Add with Subfolders. And then you're going to navigate to wherever it is that you happen to have your plugins. I happen to have mine currently on the desktop. I have ERP Lab within EEG Lab, so I only have to open the EEG Lab folder. And it's going to, because it's opening with subfolders, it's going to go grab all of those other ones. So I'm going to go ahead and select that folder. And what you'll notice is all of these paths now change. They're all going to find that folder and all the subfolders within it. If you have the ability to save this path, go ahead and do that. Then you don't have to go through this step at the beginning. In a lot of cases, if you're using a school computer, for example, it will not let you do that. My computer won't even let me do that, and it's my computer. So I'm going to go ahead and hit close. It will save those paths for my use right now. And it's going to ask me if I want to save them. And I'm going to say no, only because I know if I say yes, it's then going to yell at me that I don't have that privilege. So now that our paths are loaded, I'm going to go ahead and type in EEG Lab, all undercase, and that is our program. So it's going to pull up EEG Lab and ERP Lab at the same time. And it's going to go through a lot of stuff in the background. This is our MATLAB console. We'll be looking at that from time to time, but mostly we're going to be working in this GUI. And you'll see there are some warnings. If there are some warnings, don't worry about it. It's fine. All right, so we're going to be working in EEG Lab. Another just note, sometimes ERP Lab is all the way on the left, sometimes it's in the middle. It depends on the version you have loaded at that time. The first thing we're going to do is we're going to import our data file. So I'm going to be using raw EEG data from BrainVision. If you happen to be using a .set file, you're going to be loading an existing data set, but we have a raw file. The files themselves, if you're copying them from somewhere, there should be 3 of them. Sometimes people think, oh, you only need the .eeg, but you actually need all 3. So make sure you have them all. But we're going to go use an EEG function and plugin for BrainVision specifically. And then we're going to navigate to our data file. I happen to already be where I need to be, and this happens to be one of the data sets. If you happen to be using the Pursue materials, this is the N400 data that we use with the labs, and this is subject 1070. So I'm going to go ahead and click open. And what you'll see is it asks you some questions. It's okay to click OK on this. You don't have to do anything in particular. It will load it. And we will have to name it. So I'm going to give it just the name of the participant, which is 1070. And you'll see things happening in the background. But what's important is now we have a data set. It says number 1, 1070. And if I click on data sets, I'll see my data set. Whichever data set I'm currently working with, there'll be a check mark next to it. I also know it's uploaded because there's things now in these different descriptors of the file. I can also just plot it to see if it's actually there. This is a plot function in EEG Lab, and you're going to go ahead and say channel data scroll, and it will pull up your data. Now, I have not DC corrected my data, so I only have 1 line here, but I do know it's actually loaded because there is something there. All right, so the next step is actually filtering our data. This is an ERP Lab function, and we're going to go into Filter and Frequency Tools, Filters for EEG data. Once we pull this up, you'll notice a number of things. We have that kind of image of what it thinks it's going to be doing to our data, and then a bunch of buttons we might play around with. One is the filter type. We're going to be using the Butterworth filter, but if I were going to be doing a notch filter, I might click on the Parks McClellan notch. Just to show you what this does, I'll click on it, changes this, and so we can see, it's pulling out 60 hertz noise. It also messes around with some things down here, which I'll explain in just a second. So I'm going to go ahead and put it back on an IR, the IIR or 2R Butterworth. We're not going to worry about the display or the roll-off or any of that right now. What is important is that we are removing the mean value or the DC bias before filtering. So if this radio button is not clicked, make sure it is clicked. Right now, because I messed with things above, I have a high pass filter that's on and a low pass filter that is off. I know it's off because it's gray versus yellow, and I'm going to go ahead and click that. It's going to yell at me, but that's only because my high pass filter is so high and my low pass is so low. So I'm going to change these numbers and it will no longer yell at me. It will go back to what it was looking like when I first opened it. And that's because I have now a high pass filter of 0.1 and a low pass of 30. And so this is kind of a default of what you might use for filtering. You're going to play around with this, or you should play around with this to see what it's actually doing to your data when you change the low pass or the high pass filters. So I've got that all set. I'm going to go ahead and click apply. And it's going ahead and filtering my data. And now it's saying it's going to name it with 1070_filt. The nice thing about this program is it will stick on a little tag to tell you what you just did with your data, which is really nice. You also can save it as a file somewhere else if you wanted to. So if I wanted to save this to my desktop, if I needed to have this for another time, I could do that. I'm not going to do that right now, but just wanted to show you, you can do that. What you will have to do sometimes, not always, it depends on your version, it depends on a number of different things, is you may be asked to save the old data set. And this you should do. And the reason you want to do this is because otherwise it will not appear in that list of data sets. And I'll show you that in a second. So usually I just save this with the name prior. So 1070 in this case. So now we have data set number 2. Now, if I go back, you'll see data set number 1, data set number 2. And if I had not saved, it would have just rewritten over that data set 1. So I now have both. So this, I now have a filter. I want to plot it and look at it. So I'm going to go back to plot in EEG Lab. And now you can see all of my electrodes are showing up. There are a couple of really important things about channel data scroll that are helpful. One is these left and right arrows here. This is time in seconds, and so I can walk through my data in time. You don't want to just look at one point, you want to look throughout it. The other thing is the scale. So right now it defaults set to 84. It'll kind of default set to your data, what it looks like, but you might want to make these larger or smaller. It's not changing your data, it's just changing the viewing of your data. So if I, for example, went down to 50, it's going to make them bigger. Let me even go down smaller or bigger so you can see. Now they look really large, and you can go the other way as well. So sometimes if you can't see something's out of range, you might want to make a bigger number so that you can actually make them smaller and see them. So the important thing to note is you can change this, but if you're comparing between two sets of data, you want to make sure the scale is the same, because if you're trying to compare two sets of data and they're at different scales, it's not easy to compare them. So this is what you can do and look at it. If you then want to go back and refilter the data at a different, 0.1 to 150, for example, you can do that. You just want to go back to your earlier data set, the one that says filt. You don't want to filter an already filtered file. You want to filter the raw data set. So you just click on that and it's going to say, oh, what do you want me to do with this file? You're moving away from it. Again, you may not be asked this, but if you are, you just want to go ahead and name it. And I'm naming it filt because that's the one I just was on. And it's going to then go back. And I can see I'm now on data set 1, which has not been filtered. And I can then do that again. I can filter my data. but maybe I'll change it. So maybe this time I would do it at 150, for example. And once it's done that, it'll ask me to save it. I'd recommend giving it a different name so that you know what you have and what you're looking at. So now I have 3 data sets. I have the raw unfiltered. I have the filtered with that first 0.1 to 30, and now I have one that's 0.1 to 50. And I could plot that and I could compare them. You can have 2 different channel data scrolls open at the same time and even compare them side by side. So that's all I wanted to show you today. We'll keep going another time, but in the meantime, good luck.